Welcome back, and thanks for being here. On this channel, we start with real science, follow the evidence, and explore the mysteries that still don't have answers. If that's your kind of story, like, subscribe, and turn on notifications. Now, let's get into it. January 1st, 2026. The holiday skies are clear over most of the northern hemisphere, and the telescopes are still turned outward. The data stream from December 19th is complete now, locked into the archives of every major observatory on Earth. 3i Atlas has already passed its point of closest approach. The event itself lasted no more than a few days, yet it will occupy astronomers for decades. The object is already moving away, receding beyond the orbit of Mars, dimming each night, becoming again what it has always been, a faint streak against the deep background of stars. The story of this visitor began quietly. It appeared in mid-year surveys, just another slow-moving blur in the background field of automated sky scans. At first, there was nothing remarkable, until analysts noticed the trajectory. It was not closed, not looping around the sun, but open, a hyperbolic curve that meant only one thing. This object came from outside the solar system. It was the third time in recorded history that humanity had identified such a traveler. After Oumuamua in 2017 and Borisov in 2019, this one was cataloged with a name that sounded both technical and mythic. 3i Atlas, the third interstellar object discovered by the Asteroid Terrestrial Impact Last Alert System. Each discovery has pushed against the boundaries of understanding, but this one has done more. It has stayed long enough and bright enough to be studied in detail, and the detail has refused to settle into any simple pattern. On paper, it behaves like a comet, expelling gas as it warms, brightening as it nears the sun. But in its wake lie measurements that contradict the models built to explain it. The object's surface albedo, its emission spectrum, the rhythm of its brightness, they do not fit. Observatories from Chile, Hawaii, and orbit have turned their lenses toward it, searching for a coherent story in the changing numbers. NASA's official summary describes a natural body rich in carbon and volatile ices, releasing plumes of gas through solar heating. The description is reasonable, consistent, and reassuring. Yet, within the data are signals that are neither random nor fully natural. What stands out most is not what was seen, but how it changes. Every image reveals something slightly different. A brightness surge here, a sudden spectral line there. The pattern implies a system with internal order, something adjusting to its environment rather than simply eroding under it. And now, as it moves away, the debate begins. The physical encounter is over. The intellectual one is only beginning. Observatories are already scheduling time to reprocess the images, to look again at the faint jets that appeared in late autumn. The Webb and Hubble teams are comparing light curves, searching for thermal echoes that might reveal what lies beneath the crust. What happened on December 19th cannot be repeated. The closest approach has passed, and with it, the last moment for direct study. But its traces remain, fixed in the data, waiting for interpretation. Each record becomes a fragment of an unsolved question. What kind of visitor passes this way once in a civilization's lifetime, and leaves behind more uncertainty than before? The answer will not come soon. The object is moving at more than 30 kilometers per second relative to the Sun. By March, it will cross the orbit of Jupiter and fade into the outer darkness, beyond reach. What remains now is a paradox, a confirmed observation that resists full understanding, a fact that feels like a mystery. The new year opens with that mystery intact, drifting silently beyond the range of our best instruments. From July of the previous year, the faint track of 3i Atlas had been under observation by networks spread across 3 continents and by telescopes beyond the atmosphere. The Atacama Large Millimeter Array in Chile traced its chemical lines. The Hubble Space Telescope recorded its reflected light, and instruments aboard the Mars orbiters caught its silhouette as it passed the plane of the red planet's orbit. The raw data filled terabytes, every reading cataloged, calibrated, and compared. Yet after months of analysis, the composite image still refused to converge. 3i Atlas looked like a comet and behaved like one in certain aspects. A diffuse coma of gas, a developing tail, a measurable non-gravitational acceleration caused by venting. But at the same time, several parameters diverged sharply from those of any known cometary body. Its rate of brightening as it approached the Sun exceeded predictions by a factor that no dust model could explain. The spectrum showed strong carbon signatures, but also spectral gaps where known compounds should have appeared. Observers expected noise or instrumentation error. Recalibration brought no change. By early December, astronomers from NASA and the European Space Agency coordinated simultaneous observations to check each other's data. The results matched. The anomaly was real. The official public update described it as complex activity characteristic of carbon-rich interstellar material, a phrase that explained nothing and avoided speculation. Beneath that restraint, private discussions turned toward possibilities that no one wanted to put on record. Some patterns in the light curve suggested internal periodicity, pulses repeating over intervals too regular for random surface outgassing. Others noticed that the direction of the object's faint jets appeared to change in sequences matching its rotation period, as if coordinated rather than spontaneous. Statistical coincidence was the conservative answer, and most reports stopped there. But a few analysts persisted, comparing the data with simulations of controlled thrust or timed venting. The resemblance was unsettling. What made this case distinct from the earlier interstellar visitors was its brightness and persistence. Unlike the tumbling shard that had been Oumuamua, or the diffuse ice cloud of Borisov, 3I Atlas maintained a stable light curve for months, its core remaining intact even after perihelion. The stability implied mass, density, and perhaps structure. When researchers plotted its trajectory backward, the path extended far beyond the boundaries of the Oort cloud, back into the void between the stars, to regions where gravitational tracing loses meaning. No origin point could be assigned with certainty. The object could have drifted for millions of years. It could have come from anywhere. What remains certain is its speed. At 30 kilometers per second relative to the Sun, it is moving faster than any spacecraft humanity has ever built. At that rate, each second carries it further from verification, deeper into speculation. As it passes the orbit of Mars and heads toward Jupiter's path, the margin for direct measurement shrinks. Only instruments with extreme sensitivity can still register its fading emissions. For the teams involved, this creates a dual reality: complete data collection and incomplete understanding. The numbers exist, solid and repeatable, but what they describe is ambiguous. Every interpretation requires an assumption about what kind of object is being observed. If the assumption is wrong, the conclusions collapse. The institutions responsible for public communication choose caution. They release graphs, light curves, and chemical models that reassure. They avoid the words that might ignite premature excitement. The narrative remains simple: a comet from another star, unique but natural. Yet within observatories and mission control rooms, the tone is different. Scientists are trained to resist speculation, but they are also trained to notice when something does not add up. 3I Atlas sits precisely in that uncomfortable space, too consistent to ignore, too strange to categorize. As it moves beyond Earth's orbit, it carries with it not only dust and gas, but a growing unease, the sense that something fundamental has been seen, but not yet recognized. The chemical signature becomes the first clear fault line between the comforting story and the uneasy one. In the weeks after the closest approach, on December 19, 2025, analysts return again and again to a single measurement because it refuses to behave like a normal detail. Methanol appears in the plume. Methanol itself is not exotic. It is a small organic molecule found in cold environments and in many comets, a piece of basic chemistry that can be assembled on dust grains in interstellar clouds and preserved in ice. The problem is not that methanol exists. The problem is how much. Radio observations reported from the Atacama Large Millimeter Array point to a release rate on the order of 40 kilograms every second, sustained rather than momentary, as if a deep reservoir is being opened and kept open. For a typical solar system comet, methanol appears as a minor ingredient, present but not dominant, rising and falling with the season of sunlight and the uneven exposure of fresh ice. For 3I Atlas, the outflow seems too strong, too consistent, and too difficult to reconcile with simple surface frost being warmed and escaping. The clean explanation says the object is rich in carbon-bearing ice, and it is responding to solar heating in an unusually active way. That is possible. Interstellar material can preserve chemistries that differ from the local recipe. A comet born around another star may carry ratios that look strange beside familiar comets shaped by the Sun's formation environment. Still, even within that framework, the numbers press hard. To keep releasing that much methanol, there must be either an enormous surface area of active vents or a mechanism that delivers fresh volatile material to the surface without rapidly sealing itself shut. Either option implies a body that is not a loose pile of rubble. A porous, fragile aggregate tends to collapse as jets open channels and as the outer layers erode. It sheds material, changes shape, tumbles, and often breaks. Yet the observations keep returning to stability. The nucleus holds together through the period of strongest heating, and the jets appear in organized structures rather than in a chaotic halo. If the methanol is coming from depth, it requires pathways. If it is coming from near the surface, it requires constant renewal. Both pathways are difficult to maintain without some internal strength. That is where the second line of speculation enters, not as a claim, but as a way to make the chemistry fit the motion. Some researchers explore whether the methanol signal can be produced, in part, by chemical reactions inside the body, rather than by simple sublimation of ancient ice. One proposed route involves water interacting with iron-bearing minerals, a kind of internal processing that can create methanol under certain conditions. This idea does not require technology. It requires a metal-rich interior and the presence of liquid water, or at least transient films of water created by heating. The mere mention of iron shifts the imagination because iron suggests density, and density changes everything about how a body responds to sunlight and outgassing. A metal-rich core would store heat differently, conduct it inward, and potentially regulate the release of gas. It would also make the object heavier, less easily pushed and spun by jets, which matches the reports of a smooth departure and a modest but measurable non-gravitational acceleration. The methanol, in that view, becomes a sign of an interior that is chemically active rather than merely evaporating. But that explanation introduces its own question. What maintains the conditions for such processing in a body that has drifted through interstellar cold for ages? The interstellar medium is thin and dark. Temperatures fall near absolute zero. A traveler can remain unchanged for millions of years, preserving ice like a deep freeze. For chemistry to proceed, energy is needed. The sun provides energy during the encounter, but the strongest heating occurs around perihelion on October 29, 2025, when the object is swallowed by glare and direct observation weakens. The most important chemical event may occur precisely when the human instruments see the least. When it reappears from that glare, reports describe shifts in brightness and in color that suggest ionized gases and high-energy interactions with the solar wind. That timing matters because it offers a narrow window in which internal changes could be triggered, channels could open, or reservoirs could be exposed. If methanol outflow increases after perihelion, it implies that the sun has not merely warmed the surface, but has altered the body's internal state. If it does not increase and instead remains steady, it implies that the reservoir and its pathways were already prepared. The data does not settle that argument, it only narrows it. The object's distance near the closest approach remains vast on a human scale, on the order of hundreds of millions of kilometers, and that distance limits certainty. Even the most precise spectral lines describe gases after they have left the surface, not the physical machinery that releases them. That limitation becomes the opening through which a more uncomfortable thought enters. If a non-human system wanted to expel a volatile compound, it would not look fundamentally different at a distance than a natural vent. A telescope does not record intent. It records photons, and photons can be produced by both geology and engineering. The methanol, therefore, becomes a hinge. On one side stands the natural story, an interstellar comet with an unusual chemical inventory and strong activity under solar heating. On the other side stands a speculative possibility, an object whose outflow behaves like controlled release, either because the physics of its structure channels the gas in unusually stable ways, or because the release is not purely driven by sunlight and random fracture. Between those extremes lies a middle ground that is harder to dismiss than it should be. The middle ground says the body may be natural, but unusually coherent. A dense nucleus wrapped in an insulating shell, with deep volatiles that do not behave like the shallow frost of familiar comets. In that middle ground, the methanol outflow is neither fuel nor message, but it still signals something rare, a piece of another system whose internal composition and structure are unlike the fragile ice balls humanity has cataloged for centuries. That alone would be enough to justify urgency. Yet urgency cannot create a mission in time. By January 1st, 2026, the object has already crossed the point where its most intense chemistry occurs, and the strongest signature is already fading. The methanol continues to stream, but each hour carries it farther from the sun, farther from the conditions that make it visible, and closer to the moment when the last detectable line collapses into noise. The surface of 3I Atlas remains one of its most stubborn puzzles. Every major telescope that has managed to isolate its reflected light finds the same thing, an unusually dark, nearly featureless spectrum. the kind associated with carbon compounds baked under radiation for unimaginable spans of time. That darkness is not just a color, it is a property, a physical shield that absorbs sunlight, resists rapid heating, and hides everything beneath. The models call it a crust, but crust is an incomplete word. This outer layer may be 20 meters thick, formed from carbon chains hardened by cosmic rays during millions of years between stars. Such a layer changes how the interior behaves. It slows heat penetration, moderates expansion, and delays sublimation. A comet covered in this material would not respond to sunlight as a fragile body does. It would endure, venting in a measured way rather than erupting. The crust would act as a regulator, creating predictable jets from deeper cracks while preserving the main body. This scenario aligns with what observers have seen: stability in motion, jets that switch on and off but do not destroy the structure, and survival through the extreme temperature gradient of perihelion. For some scientists, this fits comfortably within natural physics. The universe is capable of creating such materials. Organic compounds on icy grains can polymerize under ultraviolet light and particle bombardment, turning into asphalt-like solids that become protective skins. Interstellar radiation only deepens that transformation. But for others, the same properties raise a more complex possibility: a thick, carbonized shield that preserves volatiles within, surviving the heat of a star without disintegrating, looks functionally like an engineered heat shield. It is not necessary to claim intention to note the resemblance. In engineering, carbon composites are chosen for their endurance. In nature, the same compounds arise through exposure. Both routes produce the same outcome: resilience. The question becomes whether the resilience of 3I Atlas is coincidence or something more deliberate. As the object approached the Sun in late October, instruments predicted fragmentation. A body several kilometers wide, with active jets and internal pressure from heating, should begin to shed pieces. It did not. When it re-emerged from the glare, it was brighter and intact. That survival forced recalibration of assumptions about its density and strength. If the dark crust were simply dust and tar, it would have cracked. Instead, it absorbed the stress. Thermal models now estimate that the interior remained cold even when the outer layer faced solar radiation intense enough to vaporize surface ice. The heat that did enter seems to have been redirected into controlled venting through narrow jets, which relieved pressure without destabilizing the core. These are the same dynamics that would be sought in a durable, long-distance probe: the ability to manage heat, regulate internal pressure, and expel material without losing shape. The natural explanation remains strong, but the coincidence of outcomes is striking. The layer also complicates observation. Because the surface is so dark, visual imaging fails to reveal topography. No craters, no ridges, no rotation markers. Only faint texture variations in infrared, possibly due to uneven outgassing. The result is that no one can tell whether the object is spherical, elongated, or irregular. The shape must be inferred indirectly through light curves, which depend on how reflected sunlight varies over time. Those curves, however, are unusually smooth. They lack the deep oscillations that would come from a body tumbling or having strong asymmetry. That steadiness implies either an orientation that keeps one face toward the sun, a rotational state locked by internal mass distribution, or an inherently balanced geometry. Each explanation points again to unusual coherence. The crust is part of that coherence. It is the memory of the object's journey, written in radiation scars, but it also acts as armor, preserving secrets beneath. Within that armor may lie layers of ice and rock unchanged since the birth of another star system. Or, if one follows the most speculative line, it could contain structures, voids or chambers, that serve some function not yet understood. Without physical sampling, there is no way to tell. All attempts to model interior composition depend on indirect emissions, and those emissions are dominated by the same handful of volatile compounds. The uncertainty leaves room for imagination, but imagination is not evidence. The data only confirms that the surface resists erosion far better than expected, and that the object holds itself together under forces that would destroy ordinary comets. Each property reinforces the next: dark color, high thermal resistance, smooth motion, unbroken stability. Together, they form a profile of something that behaves more like a designed capsule than a random cluster of dust. The scientists involved avoid that comparison in their papers, but the thought remains. A natural traveler may look accidental and still function perfectly, because evolution through cosmic time selects survivors. Perhaps 3I Atlas is simply the survivor archetype, a fragment that endured interstellar exposure longer than any other, shielded by its hardened shell. Whatever its origin, the dark crust is both its signature and its mask. As it recedes, that mask continues to block vision, leaving the instruments to record only what escapes from beneath: fleeting gases, fading light, and an unbroken surface that absorbs every answer before it can be read. The first time the tale becomes undeniable, it feels like a turning point, because it is the moment when the object finally starts to look familiar. A tail is an old symbol in astronomy, a sign that sunlight is doing what it always does to cold material, turning ice into gas and pushing dust outward with radiation pressure. When 3i Atlas develops a dust tail, the natural story gains momentum. A comet from another star has arrived, and it is behaving like a comet. Observers measure the tail's angle relative to the sun, compare images night by night, and watch the coma expand. The tail is not a solid thing. It is a shifting pattern of particles, each grain following its own path. Dust is heavy enough to lag behind the nucleus, while gas can be pushed into a narrower, brighter plume. In most comets, these features are messy. They vary with rotation, and with uneven patches of volatile material. What makes 3i Atlas uncomfortable is that the mess has structure. It does not only produce a single trailing band. Over time, images suggest multiple components, different streams overlapping, sometimes separating into faint filaments. A normal explanation exists for nearly every part of this. The sun heats one region, a jet opens, dust follows, the nucleus turns, the jet turns away, then another patch wakes up. The pattern can look organized even when it is not. Yet a second feature appears that does not settle as easily in the mind, even when the physics is known. Around mid-October of 2025, observers report an anti-tail. It is a spike of light that seems to point toward the sun rather than away from it. Anti-tails are rare but real. They are not truly pointing into sunlight. They are a trick of perspective. When Earth crosses the plane of the comet's orbit, dust that has been spread into a flat sheet can be seen edge on. The sheet lines up in the sky so that it appears to extend sunward. This is a geometric effect, and it has been documented many times. The problem is not that the explanation fails. The problem is what the explanation resembles. A sunward spike looks like braking. It looks like a controlled counterforce. It looks like something pushing against motion rather than surrendering to it. Even when every astronomer knows the anti-tail can be natural, the visual impression lingers because it matches a different story too well. The mind holds two images at once: dust geometry and deliberate thrust. In most cases, the first image wins easily. In this case, it does not, because of everything else that surrounds it. The anti-tail appears in the same season when other unusual features strengthen, including the reports of multiple jets and a deviation from predicted motion. It becomes less of an isolated curiosity and more of a part in a wider pattern. The timing also matters. The object passes close to Mars on October 1st, 2025, within tens of millions of kilometers, a distance that counts as near on the scale of planets, but still far beyond reach. The Mars orbiters observe it as a faint glow against the thin Martian sky. The object survives that passage without the dramatic fragmentation expected from an actively venting nucleus entering the inner solar system for the first time. Shortly afterward, the tails emerge in clearer form. The sequence invites a simple interpretation. It warms, it activates, it releases dust, and the system becomes visible. Yet the same sequence can be read as adaptation. It approaches, it tests its environment, and then it changes its behavior. That is not a claim of intent. It is a description of what the data resembles. The more conservative reading says the object contains volatiles sealed under a hardened crust, and only after heating does it open vents, releasing dust in a pattern that depends on internal fractures. The less conservative reading says the object switches modes, as if it is managing exposure. The anti-tail intensifies the unease because it is a feature that can be explained by geometry while still behaving like a signal to the imagination. It is a kind of ambiguity built into the sky. The dust sheet is real, the edge-on view is real, and the spike is real. But when the spike aligns with the direction of the sun, the entire scene looks like a deliberate act, even if it is not. For scientists trying to communicate clearly, that is a problem. A public image that resembles thrust invites speculation that outruns the evidence. But the evidence itself keeps providing openings. If the object's non-gravitational acceleration is driven by outgassing, then the direction of outgassing matters. Outgassing that points sunward at the right time could, in principle, alter the trajectory in specific ways. Natural jets can do this by chance. They can also do it repeatedly if the body's rotation exposes the same vent with the same orientation each cycle. If the nucleus is stable and not tumbling, a persistent vent could produce a consistent push. In that scenario, the antitail is not thrust, but a visual consequence of the same organized outflow that produces the measured deviation. The physics remains natural, but the behavior remains oddly coherent. The tails therefore become less like decoration and more like evidence of a system with rules. Dust and gas carry information. They reveal the size distribution of particles, the composition of the surface, the temperature of outflow, and the geometry of vents. As the object moves away after December 19th, the tail begins to thin and fade, but it does not vanish immediately. It becomes a long, delicate signature etched into space, a record of what escaped from inside the crust. The tail's shape can be traced backward to estimate when particular dust bursts occurred, like reading a trail of footprints and guessing where the traveler paused. That forensic view makes the antitail more significant, not because it proves anything extraordinary, but because it marks a moment when the geometry briefly aligns in a way that exposes the object's dust plane and suggests a kind of precision. It is as if, for a short time, the comet shows the edge of its wake, revealing that the wake is not just a random spray, but a structured sheet. The observer is left with an image that can be filed under known physics and still feel unsettled. A simple, natural explanation exists, and yet the sequence of features keeps hinting at the same uncomfortable possibility, that the object's activity is not merely chaotic erosion. It is organized release governed by a stability that comets rarely maintain. The tails, once comforting, become the first place where familiarity turns back into doubt. By early November, the images stop looking like a simple comet photograph and start looking like a diagram. The coma, once a soft halo, develops edges. The dust tail, once a single trailing band, begins to show distinct streamers. Observers describe 4 or 5 jets, sometimes more, appearing as separate lanes of material that widen as they drift away from the nucleus. Jets are normal in comets. They are produced when sunlight penetrates a weak spot in the surface, warms a pocket of volatile ice, and the gas escapes through a vent, dragging dust grains with it. A rotating nucleus can make jets appear to pulse. A changing solar angle can make one vent brighten and another fade. In the simplest sense, jets are a natural outcome of uneven heating. The detail that unsettles in this case is not the existence of jets, but how they behave together. They do not merely appear and vanish. They seem to coordinate with the object's overall stability. The streams keep their relative spacing for longer than expected, implying either that the vents are fixed in a stable orientation or that the nucleus rotates in a way that preserves the geometry. That becomes harder to reconcile with a body that should be irregular, cracking under heat, and tumbling from asymmetric thrust. A comet that is pushed by gas jets tends to spin up and wobble. It can begin to tumble chaotically, which smears jets into a diffuse fan. Instead, the jet structures on 3I Atlas appear sharper in certain observation windows, with a sense of repeatable alignment that suggests the nucleus is not losing control of its attitude. This alone does not require anything beyond natural physics. A dense, cohesive body can retain a stable spin axis. A thick crust can limit where vents open. A nucleus with strong internal strength can vent without fragmenting. But the same properties, when taken together, create a pattern that looks engineered, even if it is not. That is where interpretation becomes delicate. There is no direct evidence of mechanisms. There is only the silhouette of behavior. The most cautious approach is to treat the jets as a map of internal fracture lines. Under that approach, the vents are not random because the cracks are not random. They follow structural weaknesses created long ago, then sealed under the dark processed crust, then reopened as heat penetrates. If the crust is thick, the vent openings could be limited to a small number of persistent channels. Gas escaping through those channels would be collimated, meaning it would form narrow jets rather than broad clouds. That would naturally produce the observed streamers. A stable nucleus could then maintain those jets in roughly constant directions relative to its spin, giving the appearance of order. This explanation keeps everything in the realm of geology. Yet even within geology, the question shifts from what is seen to what must be true beneath the surface. Persistent channels imply an internal structure capable of sustaining them without collapsing. They imply either a strong, sintered interior or a core with materials more coherent than loose ice and dust. The methanol measurements intensify the issue because they imply deep volatile reservoirs and sustained release. Sustained release through fixed vents implies a system with regulated pressure. In a fragile rubble pile, pressure finds new paths, vents migrate, and the surface changes rapidly. The longer the jets remain coherent, the more the nucleus looks like a single object rather than a swarm of debris. For scientists trying to model the object, this matters because non-gravitational acceleration depends on where and how gas escapes. An outgassing jet is essentially a natural rocket. It produces thrust. If the thrust is persistent and aligned, it can shift the trajectory in a predictable way. If the thrust is chaotic and misaligned, it mainly spins the object and produces little net change. 3I Atlas shows net change without obvious chaos. That is the heart of the argument that develops quietly in the background. Some researchers, including those inclined to entertain unusual interpretations, focus on the idea of controlled thrust. They ask what the jets would look like if they were not simply vents, but exhaust. They ask how many jets would be needed to stabilize a large body moving through a gravitational field, how they would need to be spaced to counteract unwanted spin, and how they would appear when observed from hundreds of millions of kilometers away. The answer is uncomfortable because it overlaps too neatly with the observed morphology. Multiple jets spaced around a nucleus can, in principle, act like attitude control, keeping a body pointed or preventing tumble. Nature can accidentally create that pattern, but the odds become a topic of debate. Most astronomers do not frame it in those terms publicly. They frame it as a rare but natural comet with unusually coherent outgassing. Yet, the internal conversation shifts toward probability. How often does a natural interstellar object present multiple stable jets, sustained chemical release, and a smooth light curve, all while surviving perihelion without significant breakup? Each feature alone is plausible. Together, they feel less ordinary. The timing around perihelion remains a key uncertainty because direct visual observation weakens when the object is near the sun's glare. October 29th becomes a blind spot. The object goes into that glare red and relatively subdued, then comes out brighter with a different color signature and more pronounced activity. That change suggests the possibility that perihelion triggers a structural event. Cracks open, vents reorganize, the crust fractures in controlled ways, or buried volatiles become accessible. If that is what happens, then the jets seen in November may not be a continuation, but a new phase. A new phase implies a transition. A transition implies that the object responds to the star, not just by heating, but by altering how it releases material. Even if that response is purely physical, it resembles adaptation. It resembles a system shifting into a different operating mode under new conditions. The word operating is usually reserved for machines, but in this context, it becomes difficult to avoid because the behavior is not merely passive. It does not simply erode. It activates, then organizes. As the object moves away after December 19th, the jets begin to fade, but they do not instantly disappear. They diminish as sunlight weakens and as the reservoir cools. That fading can be modeled. The models say the jets should shut down as the object approaches Jupiter's orbit and the sun's warmth becomes too weak to sustain outflow. Yet even here, uncertainty persists. If the jets are driven only by solar heating, they should follow a predictable decline. If they are driven by internal chemistry or by processes unrelated to simple heating, the decline could be delayed or irregular. Observers watch for that irregularity. The possibility remains that the jets might flare unexpectedly, or that one streamer might persist longer than the others, suggesting a deeper, warmer channel. In a natural framework, that would be evidence of uneven insulation and internal layering. In a speculative framework, it would be evidence of active management. The data alone cannot choose between these. It only keeps the door open. In the end, the jets become the most visible expression of the object's ambiguity. They are the clearest sign of activity, and yet activity is precisely what can be interpreted in multiple ways. A venting comet is active. A guided probe is active. A natural body with unusual structure is active in a different sense, driven by physics that looks like intention from a distance. The jets make that ambiguity unavoidable because they turn the sky into a pattern that looks almost like design, while still remaining fully compatible with nature's capacity for rare configurations. The argument about motion begins as a technical footnote and slowly becomes the central tension, because motion is one thing that cannot be faked by interpretation alone. Light can mislead, Color can shift with viewing angle. Tails can form illusions through geometry. But a trajectory is a trajectory. It is governed by gravity, and if it departs from prediction, something has pushed it. For comets, that push is well known. Sunlight warms the surface. Ice turns to gas. Gas escapes, and the escaping gas acts like a tiny engine. This is called non-gravitational acceleration, not because gravity disappears, but because a second force adds itself to gravity's clean math. In most comets, this extra force is messy. Jets do not fire evenly. Vents open and close. The nucleus spins, and the direction of thrust changes constantly. Over time, the pushes average out, or produce unpredictable deviations. The effect can be measured, but it is rarely smooth. That is why the reported deviation for 3I Atlas draws attention. After perihelion, the object's path differs from the purely gravitational prediction by a small but real amount, on the order of a few arc seconds. On the sky, that is tiny, a shift that would fit inside the apparent width of a coin held at arm's length. In orbital calculations, it matters. A few arc seconds can correspond to thousands of kilometers of difference over a long arc of travel. The number itself does not imply intention. Many comets show such deviations. What makes it notable is how it pairs with the object's apparent stability. If a body is being pushed by outgassing strongly enough to create a measurable deviation, it should also show signs of the push in its rotation. The jets should torque it, spinning it up or tipping its axis. Over weeks, the light curve should become erratic as the object tumbles. Instead, reports describe a light curve that remains relatively smooth and a coma structure that retains coherent jets rather than smearing into chaos. This is not proof of control. It is a mismatch between the behavior expected from a fragile, irregular comet and the behavior implied by the observations. There are natural ways to reduce torque. If the jets are arranged symmetrically around the nucleus, their sideways forces can cancel, leaving mainly forward thrust. If the nucleus is dense and massive, it resists being spun by the same force that would easily tumble a smaller, lighter object. If the vents are confined to specific latitudes on a stable spin axis, the net effect can be consistent. These are real physical scenarios, and they are plausible, especially for a large body with a thick insulating crust that limits where activity can occur. Yet plausibility does not erase the unease. In the context of an interstellar object, every natural scenario carries an additional burden. It must explain not only the behavior, but why such a configuration survives the long interstellar journey and then presents itself in the inner solar system at the exact moment it can be observed. That burden is not scientific, but psychological. It is the feeling that rarity is piling on rarity. The deviation becomes a magnet for speculation because it is a clear, measurable effect that invites a question with only two broad answers. Either the outgassing is unusually well organized by chance and structure, or the outgassing is organized because something organizes it. In the first case, 3I Atlas is a natural object that happens to be shaped and vented in a way that produces a clean net push. In the second case, it behaves like a vehicle. That second interpretation is not asserted by the data, but it is implied by the language people use when they try to describe what they see. They speak of course correction. They speak of smooth departure. They speak of stability as if stability is a choice. These words are metaphors, and careful scientists avoid them. Still, the calculations themselves carry the same implication without the language. A consistent, non-gravitational acceleration is equivalent, in effect, to a weak, continuous thrust. If the thrust points in a particular direction relative to the object's motion, it can change the shape of the trajectory. The question then becomes whether the direction of thrust matches what would be expected from sunlight-driven outgassing. In comets, the strongest outgassing usually occurs on the sunlit side, producing thrust that tends to push the nucleus away from the sun. The exact direction depends on rotation and thermal lag. For 3I Atlas, the timing of the deviation relative to perihelion becomes crucial, because perihelion is when heating peaks and when outgassing should be strongest. But perihelion is also when direct observation is compromised by glare. The object is closest to the sun in apparent position and difficult to track with optical instruments. That creates a gap in the record, precisely where the thrust profile might be most informative. Analysts attempt to bridge that gap with infrared data and with models that infer outgassing rates from brightness and gas lines. The models can reproduce a deviation, but only if certain assumptions are made about vent locations and thermal properties. In other words, the models can match the data if the object is given the right kind of internal structure. That internal structure begins to resemble a designed system, not because it must be designed, but because it must be coherent. A chaotic rubble pile struggles to meet the constraints. A coherent nucleus meets them more easily. This is where the earlier details return with new weight. The thick dark crust, the sustained methanol outflow, the organized jets, the anti-tail geometry that resembles braking, the smooth light curve, the survival through intense heating. All of these features support the idea that the object is not fragile. If it is not fragile, then organized outgassing becomes more plausible. If organized outgassing is plausible, then a smooth deviation becomes less surprising. The natural story becomes internally consistent. Yet, as the natural story becomes consistent, it also becomes strange. Because it requires a comet unlike the comets that established the story in the first place. It becomes an object that acts like an engineered device while remaining natural. That is the uncomfortable synthesis. It allows the data to fit without invoking technology, but it also leaves the mind with a lingering question. Why should nature produce something that looks so much like a machine? The answer might be that nature has had far more time than engineers. Interstellar space is an environment that destroys the weak and preserves the tough. Cosmic rays bake surfaces into protective shells. Collisions remove fragile protrusions. Thermal cycles fracture and then seal. Over millions of years, only the most coherent fragments remain intact. Under that view, 3I Atlas is not a deliberate craft. It is a survivor, refined by cosmic selection. The survivor, by necessity, behaves like a capsule. It regulates heat, limits vents, and maintains integrity under stress. It produces jets that appear organized because they are forced through the few available channels. It experiences non-gravitational acceleration that appears smooth because its mass and symmetry damp chaos. This explanation is elegant and requires no extraordinary claims, yet it carries its own implication. If interstellar space filters bodies into such survivors, then other survivors are out there as well, and they may pass through again. The trajectory deviation then becomes not a one-off oddity, but a sign of a class of objects humanity is only beginning to recognize. That possibility is both reassuring and unsettling. It reassures because it keeps the mystery within physics. It unsettles because it suggests that the solar system is visited by bodies more coherent, more enduring, and more chemically rich than expected, and that each visit will carry similar ambiguities. For now, the deviation remains a small number embedded in tables, a few arcseconds of difference. Yet that small number changes the tone of everything else. It transforms the jets from mere spectacle into a potential propulsion profile. It transforms the tail into a record of thrust history. It transforms the crust from a passive skin into a structural element of a coherent body. It turns the question from what the object looks like to what it does, and what it does is move in a way that cannot be fully explained without choosing between unlikely luck and deeper order. Color is usually treated as a surface clue, a minor aesthetic detail that helps classify an object. But in the case of 3I Atlas, color becomes a timeline. The shift is not subtle. Early observations describe a deep red tone, the kind that often marks bodies that have spent long ages exposed to cosmic radiation. In the outer solar system, surfaces darken and redden as high-energy particles break apart simple molecules and rebuild them into complex carbon-rich compounds. That process can take millions of years, and it leaves a signature that astronomers recognize immediately. A red interstellar body, on first approach, fits expectation. It suggests long isolation, cold storage, and a surface altered into a tough, inert skin. Then the object begins to approach the sun more closely, and the color changes. Green appears, and green is also familiar in comet science. Certain carbon-bearing gases can glow green when excited by sunlight, and comets in the inner solar system have shown green coma before. Green does not imply anything extraordinary. It suggests that a new layer has awakened, that volatile compounds are escaping and fluorescing as they are broken down by ultraviolet radiation. Up to this point, the sequence still supports the official narrative. A comet-like object warms, vents, and displays the typical colors of excited gas. The trouble begins with the next step. Blue emerges after the most critical moment, and the timing forces attention onto what is not directly seen. The object reaches perihelion on October 29, 2025. At perihelion, it passes closest to the sun, and in that phase, its apparent position lies too near the solar glare for most optical instruments to track cleanly. Even with careful coronagraph techniques and space-based sensors, the view becomes compromised. The object enters a period of partial invisibility, not because it is gone, but because the star overwhelms the detectors. This is the moment when heating peaks, when internal stresses rise, when surface layers can crack, when buried volatiles can suddenly find pathways outward. It is also the moment when direct evidence thins. When 3i Atlas emerges from that glare, reports describe it as brighter, more active, and marked by a blue hue. Blue in comet imagery often comes from ionized gas, material stripped of electrons and made luminous by the solar wind. Ionized carbon compounds can glow blue. Nitrogen-bearing species can contribute as well. Blue can also be associated with very fine dust interacting strongly with the solar wind, forming a kind of plasma-like sheath. All of these are known processes, and none require anything beyond natural physics. Yet the sequence of red to green to blue carries a meaning that is difficult to ignore, because it suggests stages of activation. Red reads as inert and processed. Green reads as the first breath of warmed volatiles. Blue reads as an energized wake, a high-energy state in which the escaping material is not merely present, but transformed by intense interaction with the sun's environment. The object, in effect, appears to change character after passing through the region where observation is weakest. That change does not automatically imply anything hidden. It can be explained by the idea that deeper layers become exposed at perihelion, and that the composition of outgassing shifts accordingly. Still, the inability to watch the moment directly creates space for doubt. It creates an observational gap that becomes psychologically powerful. In that gap, all interpretations are forced to rely on before and after snapshots, and the mind begins to treat the missing frames as the most important part of the film. The color shift also connects to the earlier evidence of a thick, dark crust. A hardened, carbonized surface can suppress visible activity until heat penetrates enough to open vents. If the crust is thick, the early stage may show little gas, and the color may be dominated by reflected light from the dark surface, giving a red or brown appearance. As vents open, gas dominates, producing green emissions. After perihelion, when heating has been strongest and the solar wind is compressing and energizing the outflow, the coma can become ion-rich and appear blue. In that natural framework, the color progression is a map of depth. It suggests that the surface is not merely warming, it is being breached. It suggests that perihelion does not just increase activity, but changes the composition and physical form of what escapes. That is an important point because it implies that what is seen after perihelion may not represent what the object carries overall, only what the sun has forced it to reveal. The strongest volatile signatures, including the methanol outflow, may therefore be a consequence of the perihelion encounter rather than a steady baseline. If the sun has opened new channels, the object's chemistry becomes less like a static sample and more like a reaction unfolding in time. The brightness surge after the glare reinforces this impression. Comets often brighten near perihelion, but the brightness of 3i Atlas is described as changing in ways that challenge simple dust production models. A rise in brightness can be caused by a sudden increase in surface area of reflective dust, such as when the surface fractures and releases a large cloud of fine particles. That would be natural and common. The puzzle is that such an event often comes with fragmentation or at least visible irregularity, and yet the nucleus remains intact and the outflow retains coherence. A brightening without chaos suggests controlled release, or at least constrained release, through an architecture of vents rather than a global collapse. Again, the words controlled and architecture are dangerous because they imply intent. But the physics can still produce the same effect if the crust behaves like a pressure vessel that relieves itself through a limited number of channels. In that case, perihelion is not a time of breakup. It is a time of regulated venting. The color shift becomes a visible trace of that regulation, showing when different species dominate the coma. The blue phase also carries a hint of something else, that the object is interacting with the solar wind more strongly than expected for a diffuse cometary cloud. The solar wind is a stream of charged particles flowing outward from the sun. When it hits a comet's outgassing, it can create a narrow ion tail that points directly away from the sun, often distinct from the dust tail. The strength and clarity of this ion component depend on how much gas is ionized and on how the magnetic field drapes around the coma. For 3i Atlas, the description of a teardrop-like blue envelope suggests a pronounced interaction region, almost like a sheath around the nucleus. If that sheath is real, it implies dense outflow and sustained ionization. That is consistent with high gas production, including methanol and water breakdown products. Yet it also reinforces the sense that the object is not merely shedding material, but shaping its environment through its outflow. The coma becomes less like a mist and more like a boundary. Boundaries matter because they can hide details. An ionized envelope can obscure the nucleus in certain wavelengths, making it even harder to infer shape and surface features. Thus, the very processes that reveal activity can also deepen concealment. The observer sees color and motion, but not the underlying structure. The gap created by the solar glare repeats itself in another form, a glare of plasma and dust that hides the core. This is where speculation naturally intensifies. A cautious scientist notes that comets can show dramatic color changes as different volatiles dominate and as ionization states shift. An imaginative analyst notes that the color change resembles a system powering up, moving from dormant to active to energized after a close pass by a star. Both readings can coexist because the data supports both in different ways. The difference lies not in the photons, but in the story attached to them. If 3I Atlas is a natural interstellar comet, the color shift is evidence that it carries layered chemistry, that its crust protects deeper volatiles until the most intense heating forces release, and that the solar wind then transforms that release into a blue, ion-dominated wake. If the object is something else, the same sequence can be read as staged response, initial concealment, controlled venting, then an energized phase after a close solar encounter. This second reading remains speculative and cannot be proven from color alone. Yet color is the most human-accessible evidence, the part of the data that can be seen in images without complex processing. That visibility gives it outsized influence. People remember the red phase and the blue phase as if they are identities. In reality, they are snapshots of chemical and physical states. Still, the states occur in a meaningful order, and the order brackets a moment of poor visibility at perihelion. It is difficult to escape the sense that the most important change happens when the object is least observed. That sense is not scientific proof. It is a narrative pressure created by the structure of the observations. The year turns. On January 1st, 2026, the object is already beyond the closest approach to Earth and moving away into a colder region where activity will decline. The blue fades as ionization weakens. Green emissions drop as the sun becomes less intense. The red of the process surface begins to dominate again as the coma thins. In that fading, the color sequence becomes final. There will be no second chance to watch it repeat, no future perihelion to test whether the same progression occurs again. What remains is a record of change that looks like a story in 3 acts, with the crucial transition hidden in glare, and with every explanation resting on a single unresolved issue: whether the object's responses are merely the physics of a rare survivor, or the behavior of something that does not drift through the solar system by accident alone. The radio story begins the way modern mysteries often begin, with a rumor that spreads faster than verification. In early November of 2025, as images show jets sharpening and the coma turning more complex, messages circulate claiming that 3I Atlas is transmitting. The claim is dramatic because it bypasses inference. Light can be interpreted as chemistry, motion can be modeled as outgassing, but a radio signal feels like intent, like someone speaking. Within days, professional astronomers respond, because in radio astronomy, silence is a measurable condition and claims can be tested. Observations from South Africa's Meerkat Array add a new data layer that is at once reassuring and unsettling. The instruments register emissions near 2 well-known frequencies, around 1,665 and 1,667 MHz. These are not random numbers in radio science. They sit near the classic hydroxyl lines, spectral signatures associated with hydroxyl molecules that form when sunlight breaks water apart. When the sun's ultraviolet light hits water vapor, the molecules can split, producing fragments that then emit in characteristic ways. Under certain conditions, those emissions become amplified, creating what is called a maser, a natural microwave laser. In simple terms, the comet's coma can act like a faint radio beacon, not because it is sending a message, but because the physics of excited molecules and sparse gas can produce coherent radiation at specific frequencies. This is a known phenomenon. Comets have shown hydroxyl radio emissions before. In that sense, the debunking seems complete. The radio signal is real, but it is natural. The story should end there. It does not, because the debunking itself rests on a starting point that remains disputed. The explanation assumes a comet. It assumes water vapor in the coma, photodissociation by sunlight, and maser conditions created by the geometry and density of the outflow. All of those assumptions are plausible and, in many cases, strongly supported by the broader chemical evidence. Methanol and other volatiles imply ice. The presence of a coma and tails implies active outgassing. The sun's radiation provides the energy source. Under this framework, the radio emission becomes another piece of confirmation that 3I Atlas is doing what comets do, just with unusual intensity. Yet, the same phenomenon can be read differently if the assumptions are held lightly. A radio telescope does not detect labels like natural or artificial. It detects power at frequencies, bandwidth, polarization, and time variation. The interpretation arrives afterward. If a steady or structured emission appears at a frequency that matters in astronomy, scientists ask whether nature can produce it. Often, it can. Nature is not only capable of producing narrowband signals, it specializes in them. Maser processes exist in star-forming regions, around evolved stars, and in cometary comae. But the unease persists because the signal sits at a symbolic intersection. Hydroxyl is a fragment of water chemistry, and water chemistry is central to the story of life and to the identity of comets as carriers of primordial material. A signal on hydroxyl lines feels like an announcement even when it is not. It is the universe making noise in a language that humans have been January 1st, 2026 carries an uncomfortable clarity. The closest approach to Earth is already in the past, fixed to December 19th, 2025. And the remaining arc of the encounter is a retreat. 3I Atlas continues on a hyperbolic path that never loops back. The geometry is not a matter of debate. The object is leaving the solar system, and every day of distance reduces what can be tested. The debate therefore shifts from what can still be observed to what can still be inferred, and inference becomes a race against fading signal. The plan of the coming months is simple in principle. Track brightness as it declines. Monitor spectral lines as gas production drops. Model the non-gravitational acceleration as the jets weaken. Watch for any late surprises, any flare of activity that would imply deeper heat storage or delayed venting. The calendar is equally simple. By March 2026, it crosses the orbit of Jupiter and enters a region where sunlight is too weak to drive the kind of activity that made the object readable. After that, it becomes a faint, moving point, visible only to the most powerful instruments and only for a limited time. It may remain detectable for years as a dim smudge, but it will no longer offer rich chemistry, bright tails, or strong radio lines. It will offer mainly motion, and then even motion will become harder to separate from the background of the sky. This is the narrow exit corridor of the mystery. Whatever the object is, it will soon exist mostly as data and memory. That is why the question of origin becomes more than curiosity. It becomes the last place where meaning might be anchored, because a path backward is the only path left. Yet the backward path is uncertain. A hyperbolic orbit can be traced in the present, but over long time spans, it becomes blurred by gravitational nudges and by the fact that interstellar space is not empty. Passing stars, molecular clouds, and small perturbations make exact reconstruction fragile. Even so, teams attempt it, projecting the trajectory outward and asking what region of the sky it seems to have entered from. The results point toward a general direction rather than a precise birthplace. In popular retellings, that direction is sometimes linked to older curiosities, including the famous one-time radio burst detected in the late 1970s from the constellation Sagittarius. The coincidence is tempting because it fits a familiar narrative of a signal and then an arrival. But the most careful analysis treats this as uncertain. A wide region of sky can contain many unrelated events. The burst itself was never repeated, and the origin of 3I Atlas, even if it aligns broadly with Sagittarius in projection, does not imply a connection. Still, the coincidence remains because it reveals a pattern in human attention. When a rare object appears, the mind reaches for other rare events, seeking a thread that makes them part of a single story. The danger of that is obvious. The usefulness of it is more subtle. It keeps attention focused on how much is unknown. It reminds researchers that an interstellar visitor is not only a physical specimen, but also a test of interpretation. The object forces the question of whether humanity is good at recognizing significance when significance does not resemble anything local. This question becomes sharper when the idea of panspermia enters the discussion. Comets have long been considered potential carriers of organic molecules, water, and other building blocks. The basic mechanism is simple. Small bodies form in cold regions with ices and carbon compounds. They are scattered by planetary gravity. Some are ejected into interstellar space. Later, they pass through other systems and deposit dust and gas. Over enough time, this becomes a mixing process across the galaxy. 3I Atlas, with its strong methanol signature and carbon-rich emissions, fits this role neatly if it is natural. It becomes a messenger of chemistry rather than intention, a time capsule from another star system that briefly shares its inventory with ours. Under that view, the object's unusual coherence and thick, dark crust are not signs of design. They are adaptations produced by long exposure to radiation and cold, survival traits of a body that has traveled far. The sustained outgassing becomes not a controlled release, but a consequence of deep reserves protected by the crust until the sun's heat opens narrow pathways. The jets become not steering, but pressure relief, guided by fracture networks. The radio hum becomes not a beacon, but hydroxyl maser emission, created by sunlight breaking apart water vapor. This story is coherent, and it remains the most conservative. It also carries a quiet implication that is easy to miss. If such objects exist, and if they cross planetary systems, then exchange is real. Our solar system is not chemically isolated. It can be visited, and material can move between stars without any spacecraft. In that sense, 3I Atlas is important, even if it is entirely natural, because it is physical proof that interstellar transfer is not hypothetical. It happens. Yet, even that natural importance does not exhaust the unease, because the object has been difficult to classify without stretching the usual categories. A natural interstellar comet is expected to be unfamiliar in chemistry. It is not expected to be so stable under jet-driven thrust, so resilient through perihelion, and so structured in its activity. Those details do not prove anything extraordinary. They simply raise the cost of the simplest assumptions. As the cost rises, speculative space opens. In that space, a different hypothesis becomes harder to dismiss outright, not because evidence confirms it, but because the evidence refuses to close the door. The hypothesis says the object could be artificial in some way. It could be a probe, a fragment of technology, or a natural body altered by intelligence. Under this line of thought, the dark crust is not merely processed carbon. It is also an ideal long-duration shield. The sustained methanol outflow is not merely chemistry. It is also compatible with the idea of propellant or controlled venting. The multiple jets are not merely vents. They resemble a stabilizing system. The small trajectory deviation is not merely the rocket effect. It resembles a course correction that does not destabilize the body. The color shift after perihelion is not merely ionization. It resembles a change of state after a close solar encounter. The hydroxyl line radio emission is not merely maser noise. It is at least a signal that exists where a signal would be convenient to notice, even if it is entirely natural. None of these points constitutes proof, and every one of them can be explained by known physics. The strength of the speculative hypothesis is not in any single anomaly. It is in the stacking of anomalies into a pattern that resembles purpose. The weakness of the hypothesis is equally clear. Purpose cannot be measured from distance. It must be inferred, and inference is vulnerable to bias. Humans are skilled at seeing patterns and poor at accepting that rare natural configurations can produce machine-like behavior. That is why institutional statements remain cautious. NASA and ESA describe what can be described: a natural object rich in carbon and volatile compounds, with observable outgassing and non-gravitational acceleration. The language stays within evidence. At the same time, the evidence is not as fully satisfying as the language implies. The internal discussions persist because they are driven not by desire for sensation, but by the discipline of anomaly. Scientists are trained to follow what does not fit, because what does not fit is where new understanding often begins. This discipline becomes especially intense when the possibility of a missed opportunity is considered. An interceptor mission does not exist for this event. There is no spacecraft on the pad capable of reaching a target moving at interstellar speed with only months of warning. Even if the will existed, the physics and logistics do not. A mission designed for a later interstellar visitor may come in time for the next event, but it cannot be retrofitted to this one. The result is a form of scientific frustration that is almost physical. The object is close enough to matter, and far enough to be unreachable, bright enough to be studied, and dim enough to hide details. It offers a wealth of remote sensing and denies the one measurement that would settle most arguments: direct sampling. In this frustration, the idea of what the object might leave behind grows more prominent. Dust is already behind it, spread along its path. As Earth crossed the orbital plane, the anti-tail revealed that dust can form a sheet. That dust is not likely to fall to Earth soon, but over long time spans, orbital dynamics can bring fragments into meteor streams. It is possible, though uncertain, that in decades or centuries, small grains associated with this visitor could intersect Earth's orbit and burn in the atmosphere as a meteor shower. If that happened, it would offer a kind of delayed contact, a chance to analyze material in laboratories rather than in spectra. The chance is small, and the timeline is long. But the thought persists because it is one of the few ways the mystery could return from the dark. Another possibility is even less testable, but harder to stop imagining once it has appeared. If the object is a carrier, whether of natural organics or of something designed, then its passage through the inner solar system could involve more than gas and dust. It could leave behind microscopic material that telescopes cannot distinguish from ordinary dust. In a natural framework, this could be complex organic grains, the kind that build up in cold interstellar environments. In a more speculative framework, it could be something like sensors, fragments, or inert payloads too small to detect. There is no evidence for such payloads, and the idea cannot be proven from the available data. Yet it connects to the same theme that runs through every anomaly, the limits of observation. Humanity is good at measuring light and motion at a distance. Humanity is not good at detecting small, cold objects unless they announce themselves. A visitor that does not announce itself, if such a visitor exists, would be nearly invisible. 3i Atlas announces itself through brightness, chemistry, and activity, and still it remains ambiguous. That ambiguity becomes the final note of the encounter as the object recedes. The story does not end with an answer. It ends with an archive. Terabytes of spectra, images, and radio measurements remain, and those measurements will continue to be reinterpreted as models improve. The methanol outflow will be compared to other comets. The dark crust models will be tested against laboratory simulations of radiation-processed ice. The jet morphology will be examined with improved image processing, searching for repeating patterns that might indicate a stable vent layout. The trajectory deviation will be modeled under different thermal lag assumptions. The hydroxyl emission will be reanalyzed for subtle time structure. Each of these efforts is a way of pulling meaning from a visitor that refuses to be held. But even with perfect analysis, some questions will remain beyond reach. The core cannot be seen. The surface cannot be mapped in detail. The perihelion phase remains partly hidden by glare. The object's origin remains broad rather than pinpoint. Its purpose, if it has one, cannot be measured with certainty. As it crosses toward Jupiter's orbit in March 2026, it carries that uncertainty with it, and the solar system returns to quiet. Yet quiet does not erase the implication that the door is open. 3 interstellar visitors in less than a decade suggests either a change in traffic or a change in attention. It may mean that the sky has always been this busy and only now is being watched carefully enough to notice. If that is true, then 3i Atlas is not an isolated miracle. It is a preview. More will come. Some will be smaller and harder to detect. Some may arrive with less warning. Some may be simpler in behavior and easier to classify. Or some may be stranger still, presenting patterns that resist explanation even more sharply. The encounter therefore leaves behind a question that remains active even as the object fades. When the next visitor appears, will the instruments and the missions be ready to do more than watch it leave? Thank you for watching and for staying with this mystery to the very end. Every observation, every faint signal, every unanswered detail matters, because these rare visitors do not wait for certainty. Until the next chapter in the sky arrives, thank you for your time, your curiosity, and your attention. See you again soon. Welcome back, and thanks for being here. On this channel, we start with real science, follow the evidence, and explore the mysteries that still don't have answers. If that's your kind of story, like, subscribe, and turn on notifications. Now, let's get into it.